Hi, this is Jeff Coronado on behalf of JCSE, and this is Bridging the Gap. This is an ongoing sequence of structural engineering design tutorials that we have here in the office that are intended to assist young engineers, either young structural engineers who might still be in school and are looking to get a jump on their careers. As we all know, structural engineering is very competitive. That is to say, there's only a few slots for the for graduates, and so many structural engineers or aspiring structural engineers actually never get a chance to work in structural engineering. So this is intended for you to give you kind of a head start, if you will, on what it is that industry will expect you to know, hence the term bridging the gap, right, between what you learned in school and what you're expected to know in practice. And it's also intended for young and even not so young structural engineers who are working their way up, again, in terms of bridging the gap of what you did learn in school and what industry expects you to know. Okay, with that, let's get started. Our title today is How to Calculate Flexural Stress in Timber Manually. So this is a tutorial associated with WR1. If you have other questions that might be related to what we're covering here today, you might want to search on our channel for WR1, and you will find, you're likely to find other tutorials associated with this topic. So it might fill in some gaps on things that we may not cover here today. Okay, get all you can from a tutorial. I know that some young engineers kind of have the habit sometimes of maybe jumping around, just picking off a value that they want. That's not really the purpose here. What we want to do is to kind of bolster your career. We want to bolster your oh my goodness, your know-how as a structural engineer. With the idea being that eventually you will get to a point where you don't need to rely on tutorials. You understand how to think as a structural engineer, and that's what we're trying to do, is make you think as a structural engineer. So take this tutorial for all it's worth. Don't just extract one piece of data. Extract the way of thinking that goes into it, and that's what will most quickly get you on your path to being a structural engineer. Okay, so software availability. Well, the reason why we're going to cover flexural stress in timber manually is because not always do you have software available to you. And sometimes software can even be more tedious than running a quick check. Or you might want to do a quick hand check to check your own work. You might want to do a quick hand check to check someone else's work. So knowing the mechanics behind that quick check in terms of flexural stress in timber is probably an important tool for you to have in your tool chest. Let's take a look at the roof framing that we've got here. And one other thing that I'd like to kind of point out to you as far as your development is don't get so much into, I'm sorry, as we get into the numbers, commit numbers to memory. Okay, are you actually going to memorize these numbers? No, I'm not saying that you memorize them, but by the same token, don't just mechanically do a number and then you immediately forget about it. Like digest the number, digest each number. You know, it's kind of like if you multiply 10 times 9, let's say 10 times 9.8, right? You have a feel for what you're going to get there, right? If your answer is 1,098, you know you punched something wrong, right? The machine did something wrong for you because you have a sense of what number you should be getting. You may not know exactly what number you're going to get, but you have a sense of what number you should be getting. But you develop that because you're kind of cognizant of the numbers that you're dealing with. That's what I'm trying to get you to do here. Be cognizant of the numbers that we're dealing with, so that after a little while you get a feel for what seems right and what doesn't. Okay, you know what, I kind of skipped ahead here. We should, let me get the roof plan up. Okay, so I've pulled up the roof plan here. Now let me see if I can cloud. In particular, what I want you to pay attention to. Let's take a look at this element right here. Okay, so we have a new 2x6 roof rafter. It looks like we are spanning this rafter from here. Well, let me just continue to here. All right, so that's our span. So we've got a new 2x6 roof rafter. Now let's see. Let me clear this, and then let me switch over to the drawing. I'm going to do a distance. So that command is, get in here. That command is dist. So with that, I can check the distance between the center line of this wall, which is where this rafter is bearing, the center line of that wall to the ridge line up here. And that distance, hopefully you can see over here, is 19 feet, 8 inches. You know what, for design purposes, I'm just gonna call that 20 feet, right? We kind of round up a little bit. We don't, we tend to not deal with those pesky inches, so to speak. You know, if you have 3.5, just round it off probably to 6. If you have 7, 8, 9, just round it off to the next whole number. So typically for flexure, for spans, we probably will deal with either half foots or whole foots. Nothing in between. At most a half foot increment. I think I said that right. Okay, so in this case, let me see if we can scroll down. I think we've got a span. Yeah, we've got a span of about 20 feet. Okay, let's call it 20 feet. The rafter spacing is 2 feet. So let's go back to that. And sure enough, let's see. We can see over here that we've got roof rafters at 24 inches on center. I suppose I can do a distance command on that as well. So let me just make sure that that's how we've drawn this. So from here to here, let me see, my X distance is 1 foot, 11 inches. Okay. Oh, 1 foot, 11, 3 3/4. Sure. All right. So sure enough, I think we're confirming that our rafter spacing is 24 inches on center. All right. So let's go back here. Let's clear the screen. So we've got 24-inch spacing of rafters. All right. Determining the unit load. Okay. So we have a W dead load is equal to 11.1 pounds per square foot. And that includes the self weight of the rafter. The roof live load is 20 pounds per square foot. Now, those units loads, the determination of the unit loads, I don't want to bog down in this tutorial. We cover that in other tutorials. If you have a question, by the way, if you have a question on anything that I'm saying here, by all means, feel free to leave us a message at the end of this tutorial, and we'll try to point you in the right direction or give you an answer depending on what it is. So if you need to know how we develop the unit loads of 11.1 or where the 20 pounds per square foot comes from, leave us a note. But that's what we got here for our unit loads. So let's proceed on that assumption. Now, determining the tributary width. Sometimes tributary width, for some reason, gives some younger engineers a little bit of trouble. Let's go back to the drawing. So let's just say that we've got a rafter right here, right? And if you have questions on what rafters are, what they look like, what they do, let us know. We'll try to answer. I think that's also covered. Rafters and joists are covered in another tutorial. Then we've got a rafter right here. And then our next rafter is right here. All right, I'm only showing you 3 of these. Yes, they're every 2 feet you have a rafter, but the idea then is you want to see, to get the tributary width, you are getting the distance between those elements, and in this case, the element that we're looking at is a rafter, right? It's not a beam, it's not a column, it's a rafter. So then if we're dealing with rafters, we got to stay focused on rafters. What we want to do is get the distance, half the distance between the rafters. Okay, so in this case, let me see. In this case, half the distance between the yellow rafter and the red rafter would be this amount, right? And let me come up here. Half the distance between the yellow rafter and the green rafter is this amount. Hence, let me use this violet color. My tributary width is going to be this distance, right? Which the easiest way to get this is just getting the distance between the red rafter and the green rafter and dividing it by 2. Or in this case, since we know that the rafters are at 24 on center, we know that the tributary width is 24 inches. Because again, the distance between red and yellow is 2 feet. The distance between yellow and green is 2 feet. So if I add those two dimensions, I get 4 feet. And if I divide that by 2, I get 2 feet. So the tributary width for the yellow rafter, and hence any rafter in this project right now, is going to be 2 feet. That's our tributary width. If we wanted to look at our tributary area is simply that tributary width multiplied by the length of the rafter. In this case, the area that I'm shading in magenta becomes the tributary area of the rafter if we needed to know that. Okay, so with that, let me clear the screen. So we've got the tributary width. Now we want to determine the uniform dead load. Now remember, we've already previously established that the uniform load was 11.1 pounds per square foot, right? And now we've just established that the tributary width is 2 feet. Okay, so all I have to do to determine my uniform dead load on the rafter is multiply those two. So my uniform dead load ends up being 22.2 pounds per lineal foot. I'm going to do likewise for the live load. So the roof live load is the unit load, which is 20 pounds per square foot, times the tributary width, 2 feet. I get 40 pounds per lineal foot. Up to this point, this is independent of the design procedure that we're using. Now we have to make a decision if we're doing allowable stress design or ultimate strength. For timber, be aware, standard of the practice still appears to be allowable stress design. So even though I know that in school, what is stressed upon you is ultimate strength, that's true for steel. Steel is kind of iffy. Steel kind of goes both ways. Concrete, clearly, it's been ultimate strength for a while, but timber's probably still, the standard of practice is probably still to work in allowable stress design. So that's how we're going to proceed in this situation. And let me see, that was all right. Okay. Since this is still a standard in the industry, yes. Load combinations. Now, load combinations is covered in another tutorial. But let me just briefly stress, no, we're not following ACI 318. We don't follow MSJC 402. For load combinations, you've got to stick to the building code that is legally enforced by your jurisdiction. Okay, and those aren't ACI, those aren't the material codes. ACI, AISC, none of those material codes. Okay, so you have to go with what is legally governs in your jurisdiction. That could be the IBC. It could be something more local to you. It might be a state adopted code. It might be a county adopted code or a city adopted code. But again, the most generic one would be the IBC, and those are the load combinations that you need to comply with whatever's adopted in your jurisdiction. Okay, in our case here, since we've got a rafter, the governing load of the load combinations that govern is the dead plus roof live load. That's it, just dead plus roof live load. There's no factors on either one, or the factor is 1.0 for each. All right, so to determine the total uniform load, W, we're gonna add DNLR, and we get 62.2 pounds per lineal foot. Now we've got to look at the end supports. Well, gosh, in timber, we almost assume that everything is simply supported. I believe that the concept of simple and not simple supports in timber are covered in another tutorial. Just ask us and we'll be happy to point you in that direction. But simply, but typically most elements in timber are pin supported. So we're gonna assume this rafter is a pin support, simply supported. So our moment is gonna be WL squared over 8. And if we plug in the numbers, we get 3110 foot-pounds. Oh, by the way, remember what we talked about, right? Start thinking about these numbers. Start getting a sense for them. So we had a rafter that was about 20 feet long, right? We had a tributary width that was about 2 feet. We had a uniform dead load that was on the order of 11 pounds per square foot and a live load on the order of 20 pounds per square foot. Let's see how these numbers play out, right? We need to kind of get a feel for, at the end of the day, do these numbers check out? Are there stresses? Are there over stresses? Is it well under stressed? That way we know if we come up with something that's well under stressed, you know, then we go, wow, sure, you know, this rafter would work for 20 feet, 25 feet, 30 feet, who knows? If it's well over stressed, then okay, we start to get a feel for, okay, maybe 20 feet isn't, you know, is pushing it. Maybe these two of these rafters will work for 15 feet, maybe 10 feet, okay? Let's start to get a feel for the numbers that we're working with. So here our moment is on the order of 3,000 foot-pounds. Okay, sounds good. Let's keep on going here. Okay, the section modulus for a rectangular section, we end up with 7.56. Hopefully all of you remember BD squared over 6 for a rectangular section. If you don't, I think we have tutorials on geometric properties, so you can visit that. But for right now, let's just kind of gloss over this, assume you've got this down. So our section modulus is going to be 7.56. By the way, in case you didn't catch it, this is, and I can scroll up. No, I can't scroll up. Huh? This is for that 2x6, right? Because we have a 2x6 roof rafter. So the 2x6 gives us a section modulus of 7.56. Determine the flexural stress demand. Okay, so that's just simply moment divided by section modulus. So with that, we get upwards of 4,900 PSI if we plug in the numbers there, right? If any of this, again, if any of this gives you some cause for concern, I believe we've got other tutorials that cover all of these things more amply. So just let me know and we'll point you in the direction of those tutorials. But our stress then, our flexural stress is on the order of 4,900 PSI, okay? Determine the compression edge bracing. Yes, in a flexural member, we have to know if the compression edge is braced, and if it isn't, then what is the bracing distance? In this case, our unbraced section is 0. Okay, let me show you a section here. So here's what we've got, right? So let me see. Here's our rafter. So here is our rafter, right? All of this is our rafter. That's our 2x6 rafter. Our sheathing is right here. And that sheathing has nails that connect down into it. So we're gonna have nails here, here, right? Every so often, we're gonna have nails that connect the sheathing into the rafter. Well, that sheathing with all of these nails effectively braces the compression edge of this rafter. So if we've got sheathing, we've got wood structural panel, and it's nailed into the rafters, we can assume that the unbraced length for the compression edge is 0. All right, so that takes care of the compression edge. Determine the flexural capacity. Okay, do we have sawn lumber or engineered lumber? Well, in our case, the 2x6 tells us it's sawn lumber. But if you need help with the difference between engineered lumber and sawn lumber, let us know and we'll point you in the right direction. Excuse me. Okay, so since we have sawn lumber, then our go-to becomes table 4.3.1 of the MDS. And in that, what we see here is, and this again is covered in another tutorial. So as far as the use of these adjustment factors, but let's just focus on the one that we've got here, and that would be what I'm highlighting here in yellow. That's the flexural row for that row contains the load factors for, the adjustment factors for flexural design. Again, this is covered in another tutorial, so you can see that there are a number here of factors, right? All of these columns represent a different factor, and you can see that they are all marked. They are all marked here as being, I don't want to do white. So they are all marked as being applicable for flexure, right? However, again, what we cover in another tutorial is that most of these aren't applicable in our day-to-day design. So we cover kind of what you need to look for and what you need to spot to see if they're applicable or not. Many times these factors, as intimidating as this all may look, many of these factors just default to 1.0. So in essence, they're a non-issue. But you do have to kind of develop a little bit of a feel, understand what each one is, so that you know whether yours is going to default to 1.0 or you are going to need to take a look at it. So in our case, we've picked off the 3 adjustment factors that will be applicable to our situation, and that would be C sub D, C sub F, and C sub R. All right, so, well, let me back up actually, because actually where we do start isn't even with the adjustment factors, but it's with the tabulated bending stress. The tabulated bending stress, the tabulated allowable bending stress. Notice how for timber, we make the distinction between F sub B and F sub B prime, right? So we've got F sub B here, but we have F sub B prime here. So F sub B is the tabulated allowable stress. Did I say that right? The unprimed value, now we're making this more general, right? Whether it's allowable bending, allowable tension, allowable compression. The way the NDS works is that the tabulated value is unprimed. To that, you have to multiply it by the adjustment factors to get the final design value, which is the primed value, okay? So F sub B is the tabulated bending stress. F sub B prime is the final allowable bending stress. So to get to the allowable final bending stress, we have to multiply it by the 3 adjustment factors. But again, first we have to determine the tabulated allowable bending stress, F sub B. Well, in our case, F sub B is going to be 1,000 PSI. And again, picking off values from the NDS, and actually this is the NDS supplement, to know what is the tabulated allowable bending stress, or for that matter, any tabulated allowable stress, is a matter for another tutorial. So just let us know if that's a question you have, and we'll point you in that direction if you're not able to find the tutorial on our channel. Okay, let's move on to C sub D. C sub D then is the load duration factor. And yeah, actually, I'm sorry, I didn't write that down. I can certainly write it down here. So it's load duration factor. And there's a table in the NDS for the load duration factors. That's another tutorial. Don't want to get into the specifics of that, but in our case, it's 1.25. Then we have C sub F. This is the size factor. Again, we'll cover that in another tutorial, or it's covered in another tutorial. So let me know if you need help finding that. But C sub F is the size factors. In this case, it's 1.3. C sub R is what, the repetitive factor, I think. So we just call it repetitive factor. And what determines, did I spell that right? Repetitive. Still not right. Repetitive. Aha. No, it still doesn't like it. How come you don't like it? How do you spell repetitive? There it is. Yay, I figured it out on my own. Okay, so there's the repetitive factor. So in our case, that'll be 1.15. And again, what are the factors that go into whether something can be considered repetitive or not? There are specific criteria for that. It's not just an opinion. It's not just sticking your thumb up in the air. There is specific criteria that you need to comply with. And if you comply with those, then you've got, then you can use the repetitive factor. Again, that's covered in another tutorial, so let's not bog down on that. So with that though, now we can calculate our final allowable bending stress. So if we do the math there, we end up with close to 1900 PSI. Well, gosh, if memory serves, our demand was closer to the order of 4000 PSI, right? So big difference. Our capacity is on the order of 2000 PSI. Our demand was on the order of 4000 PSI. So let's actually do the math. Let's get the demand capacity ratio. And what we end up with is if we divide the 4935 by 1869, sure enough, we end up with 2.64, well over 1.0. So a demand capacity ratio that does not work, a demand capacity ratio that exceeds 1.0. So this section, as designed currently, does not work. So whatever it is that we had, like I think 2x6 at 24 on center, that won't work. Something needs to be changed there, whether it's the span, the spacing, the grade of lumber, but something needs to change because as of right now, that design doesn't work. But this is in essence how we would go about doing a quick spot check by hand on a flexural stress. So hopefully this was helpful to you. If it was, sure would appreciate a thumbs up to let us know that, that this was helpful for you. If you want to leave us any comments with any feedback, any suggestions that you might have that would make these more informative, more helpful for you, by all means, feel free to leave us a comment. Or if you have a question on something that you'd like to see covered that you didn't find covered on our channel, by all means, let us know. And yes, if it was helpful to you, certainly feel free to subscribe to our channel, and that way you will get automatic notifications as we upload new tutorials for structural engineering design. Okay? All right, real good, guys.